Okay, is that okay? Okay. I remember how to I think we talk about it, right? Then there's a straightforward application that not including in your textbook. I don't think your textbook talk about that, but it's called the uh, Gauss mean value theorem. Okay, so basically a very straightforward uh, application of this one. Now this is just for the Cauchy integral formula. This is a arbitrary curve going around the region that we define F is analytic. Now this in this theorem we restricted that this to a circle. So say just evaluate a circle. So you have this z sub 0 and evaluate a circle. There's a radius like R, capital R, from here, and to define a path C is a circle centered at z sub 0. And obviously still assume F is empty over all the region, including this circle. Now, we just apply this Cauchy integral formula at this z sub 0. Just apply that. Now, because we specify Z, this path C as a circle, so so yes, you know how to write Z, right? After you specify a circle, what is the expression of Z? Z, you know, but if you write it down, what is the equation of Z on the circle? Or the value of the complex number Z on this circle, how do you write it? You know? I'm looking for a quick answer. No? This is a simple manipulation. This thing should be straightforward for you. So this is the distance. All this a circular property is that all the point on the circle has the same distance away from uh, the center, right? Which is now is c sub 0. So the c minus c sub 0 should have the same distance, which is given by this capital O. The radius is R. It should be the magnitude should be R. Then obviously to keep this as a magnitude, you just add the phase that will make the magnitude is R. So all these points is specify that. I'm writing this because I need to do a little differentiation. The dz would be R created I beta y created. Okay, so this allow me to write this one. So we have this is given by this is given by that. We just substitute into here. And the path of the integral, you can now change the limit to say just over a circle. I mean 0 to 2 pi or whatever, just as long as you're going around the circle and the full circle. Yeah. The denominator is R e to I beta. Numerator is I R. This is I R e to the beta. Then obviously you know lots of cancellation, cancel I, cancel capital R, cancel e to the I beta. This is the one of the two I. That's a that's basically it's a Gauss theorem. So this, you can now interpret that as the mean of this function f along the circle, because this, you're integrating the path along the circle, evaluate the f at on the circle, or the point on the circle, and divided by the length of the circle, which is 2 pi x. I forgot this. Uh, yeah, right. There's no yeah, just evaluate this. The 2 pi is the angle because we integrate over angle divided by the full uh, 2 pi angle around at any point, right? So on the circle, so this is the mean value of fc, but the mean value is evaluated at the center. Okay, it's not on the circle. The mean of the circle, the analytic function, is evaluated at the center. Okay, so this is called. I mean, there's a name theorem of that, but yeah, it's actually it's much simpler than the theorem. But I'm talking about this because next homework, homework 2, you will have a question that if you use this, that's become apparent. Okay, so talking about this in advance.